Hello and welcome to the latest web seminar by Bitgardner. Today we'll be talking about media milling and taking a deep dive into it. My name is John Kowalski. I'm part of the marketing team here at Bitgardner, and I'd like to welcome you. We are recording this, so immediately following the presentation, you'll receive a link. Feel free to pass that around to your colleagues, take a look at it later, whatever you need to do with that. Also, if you have any questions during the presentation, please log them in the chat box. Should be in the bottom right-hand corner of your screen, and time permitting, we'll get to those questions. If for some reason we do run out of time, we'll follow up with you directly to make sure your questions are answered. So with that, let me introduce Mr. Andy Stummer. He is our business line manager for our dispersion. Andy? It's all yours, sir.
Hello and welcome everybody to our media milling deep dive today. So this is actually the second part of the last seminar that we did on the pre-dispersion part. So there's going to be a little bit of an overview of what we talked last time, and then we're going to dive right into the media milling component. Like John said at the end of the presentation, if you have questions, just type them in the chat box and we'll go through them. So a quick introduction about the company, the relationship with VMA. Then we're going to briefly discuss the dispersion process, pre-dispersing, and then dive right into the milling. Then we talk about lab and production equipment capabilities we offer, quality control. And finally, we're going to conclude showing you some laboratory capabilities here in Wallingford and as well as in Germany. So the company VMA Germany was founded in 1972 by Herman and Elke Getzmann. You can see a picture on the top right, beautiful couple. And Herman is actually still involved in the business today. He makes sure that the designers still follow his philosophy of modularity and make sure that the product line is very cohesive. Bitgardner has had the exclusive distribution rights for the VMA product line since 1988 for the US and Canada. We do all the servicing and sales out of the US, and the machines are still built at VMA in Germany. You'll see a picture here in a moment. The company is still owned by the family. The two sons, Chris and Martin, are running the business. They have over 100 employees globally, and they are represented in almost every country around the globe. They are known to make really high quality dispersers, milling systems, as horizontal mills, basket mills, and vertical bead mills for the lab space, pilot as well as production environments. So here is actually a good slide about the company in Germany. They are located about 30 miles east of Cologne, so about right in the middle of Germany. One thing that VMA stands out is their flexibility to meet customers' requirements. Basically, 40% of everything that VMA builds or designs is custom. So if you have any applications that require certain attachments or a certain design of a blade or dual shaft or anything of that nature or different rotor types, so they are able to accommodate those requirements very quickly, turn it around. We have about 8 people in the design center just designing equipment, making sure that that's a seamless process. And we also have 2 great lab spaces here in the US, actually one in the US and Canada. We're opening another one at our US headquarters for Bitgardner here in Columbia, Maryland, where we have another lab to show the dispersers and milling capabilities, as well as the one in Wallingford that's tied in with our sister company, the Big Additives group. Some of you are probably very familiar with. The great thing is we can tie in the knowledge that they offer. So it's good. We leverage those synergies between the adhesives or the additives group with our instruments group to answer all technical questions and give formulations advice and so on. So there are some advantages to having that lab space at Big USA. So here just diving right in, some different types of pigment groups that the dispersers are used for, but I want to stress it's not only pigments. There is many other end-use markets, we call them, where the dispersers and milling systems are used. For example, battery slurries, inks, 3D print media, medical applications. So there's a whole range of different end-use markets where these dispersers are used, but mainly in dispersion manufacturing, we differentiate here between the different pigment classes. So we have the organic pigments, inorganics, functional pigments, and obviously there is more and more of these special effect pigments that customers want to disperse and mill. But when it comes to special effect pigments, I want to stress we have to be very careful because we don't really want to destroy the special effect pigments. You really just want to break up the binding forces and have to be very careful, not damaging the flakes. So basically the reason why we're dispersing milling is just to improve the wetting. That's done in the pre-dispersion stage. Then we want to break up these invisible electromagnetic forces. They're called van der Waals forces. They keep those molecular structures bound together, and that's what we want to break up. And basically reduce them ideally down to the primary particle size, which actually happens when we use media mills. That will give us much better color strength, improved gloss, improved appearance. Pigment efficiency goes way up. We also have, obviously, because we need less pigments, when we're milling, we get more surface area. Therefore, we can reduce our raw material costs quite a bit if we do a proper dispersion. That will also give us much better product consistency, will lead us to formulation improvements. And finally, we're going to get a much more consistent particle size distribution, smaller particles, which will also or should give us much better upscale results when we go from the lab space to pilot to manufacturing, because we want to be really able to replicate what we're doing in the lab in our manufacturing space. So that's the whole idea of dispersing these materials and milling them. So there are some issues that come up if we improperly disperse or mill our materials. So obviously we could have a shift in our color, poor stability of our product, flocculation of pigments. So there is obviously some additives that can help with that. The Big Additives has a lot of different products for that part. Sagging, leveling, settling, some of the other issues that could come up. Reduced gloss levels is a well-known issue that comes when with improperly dispersed or milled slurries. And then obviously separation. So here you can see an example of a material that was just pre-dispersed and not milled. And then on the right side, you see a really nice milled material. So it's the same product. One is just pre-dispersed on the left, and on the right, you can see the advantages that you have when you're properly milling. Now, with the right milling technology, we're able to actually mill down all the way to sub 50 nanometers. And then obviously you will get even a more improved surface structure that you can see here on the picture. But that's some of the changes that you would see when you're optimizing your process. So it's really important to remember that we're looking here really when we're dispersing and milling for stability, because these pigments require strong color fastness to reduce fading over time. We want to get the maximum brightness, which will also give us the best color, pigment size. So in general, the smaller my particles, the better my visual. So that usually is really important. And obviously we would need less pigment because we have more surface area we are producing by milling down the material smaller and smaller. That will save you more money in terms of raw material costs. And then obviously the viscosity is really critical. Usually we are looking for the sweet spot between 1,000 to 5,000 centipoise. That's where we have really good success with the dispersing blade to get the donut effect. And then obviously for milling, We want to be also as low as possible, not too low, otherwise it's more difficult to put in energy into the slurry or mill base. So between 1,000 and 5,000 centipoise, that's usually a really good sweet spot. We can still mill with more viscous materials as long as the material flows, but when it gets to become more pasty, then it's a lot more challenging. So that would preclude us from using certain milling technologies, like a basket mill, for example, where the material wouldn't flow into the milling basket. So you would need more like a horizontal bead mill. And for that, there is different types of plunger systems instead of a pumping system to get the slurry pumped through the milling chamber. But that's something that depends then really on the flow characteristic, the rheology of the material, and the viscosity that you have. Something we could test out in our lab in Wallingford in Germany. So it's really important to remember when we talk about dispersing and milling, we're really only trying to reduce the particle size. We don't want to destroy the particles. So it's about breaking up these binding forces, these van der Waals forces that keep these particles clumped together. So these agglomerates and aggregates are reduced to primary particles. So when we're pre-dispersing, we are reducing our agglomerates to the aggregates. That's done with the dispersing blade. And when we're actually milling, then we turn the aggregates down to the primary particle size. You can't take an aggregate and use a Cowles blade and think you can get down to primary particle size. The Cowles blade is very efficient as a pre-dispersing tool, but not really good as a fine dispersing tool because we're just not able to put in enough energy and shear rate to really break up the binding forces of these aggregates to break them down to primary particle size. So it's really imperative to have media and a milling system to really get to that point. And then it's always the shear forces really that are responsible for that separation, nothing else. And finally, we always need to keep in mind that we need the right additives to keep our slurry in suspension. So here is an example of different types of pigments, just giving you an idea of what they look like under the microscope. And there's a great slide just explaining in detail how we're going from very large clusters down to primary particle size. So the agglomerates, which is the bigger building blocks of these pigment clusters you see here, you can go with the dispersing blade and really break them up nicely, turning them into the aggregates. But when I want to go from the aggregate level down to the primary particle size level, I really need to use that the milling tools that I just explained to further break up these binding forces and reduce the particle size. So this is a great slide showing you just the process. So wetting and pre-dispersing, we use the blade. And then for milling, we have different milling tools, obviously, that really gets us to the primary particle size and at the end to stabilize the process with the right additives. So here is the actual threshold chart where you can see the limitations of just using a Cowles blade with a dissolver. So maximum is about, or minimum is about 10 microns of particle size. Anything less, we absolutely have to do milling. So if you're looking to go down 2 microns, 3 microns, or even smaller in the nano range, then definitely we need to use a milling system. So here you can see the different types of technologies that are available with BIC. So we have for the pre-dispersion, Dispermat CLC, CVC, and AE range. You'll find all the information online or let us know what you're interested in. We can discuss it with you. And then for fine dispersing, obviously, Dispromat SL is our laboratory workhorse. And then for production, we have the RS line for horizontal mills, for basket mills, the Dispermat TML for the lab space, and then for production, the SC combined with the quick change system. And then for vertical bead mills, we have the milling system. APS will also cover that today as well. Really important to remember when you're milling and grinding, our tip speed is less than that when we are pre-dispersing, or we're talking about 18 to 25 meters per second. In milling, we are going to reduce our tip speed or rotor speed down to 10 to 16 meters per second. Everything else is Too slow is not going to give you milling efficiency. Too high of a tip speed, law of diminishing return. We're not really gaining much by increasing the speed, except we're wasting more energy. So here, obviously, just a refresher, the diameter of our vessel size is really important. When we're pre-dispersing, always 1/3 to 1/2 of our vessel should be the diameter of the blade. Tip speed calculation, that's very important also when you're calculating the speed of your rotor when you're milling. So that's actually the velocity of the blade, the velocity of the RPMs. Multiply that by pi, as well as the diameter of your rotor or your blade, and if you want to calculate it for pre-dispersing, and divide everything by 60, that would give you the calculation for meters per second. And that's what you're looking for when you're milling. 10 to 16 meters per second is the optimum milling window to optimize the milling process. Donut effect, you can see it right here. When we're pre-dispersing, visual cue, always like to see a donut. And obviously, when we are using our pre-dispersing tool, the cow's blade, which is the step before we are milling, we always want to be between 18 to 25 meters per second. 1/3 to 1/2 of the diameter of the vessel should be the size of the blade. Obviously, 50% fill rate is recommended in the container. Watch your pigment filler concentration. Try to keep the temperature as low as possible, especially when we are milling. We're going to put in a lot of energy into a mill base, so that's a lot more critical than when you're pre-dispersing. So have the right chiller ready, and double walled vessels are always important when we are milling. And obviously, again, the dispersing agents that we need to put in to really ensure that we have improved wetting and no flocculation of our particles. And then when we reach about 10 microns, that's when we start going into the bead mill, where we're able to put in a lot more energy. We then really break up the binding forces of the aggregates to further deagglomerate down to the nano range if we need to. And that's basically giving us the best performance of our product, color strength, transparency, particle size distribution, and so on. So this is actually what happens here inside of a bead mill. So you're loading up a milling chamber with beads. You have a rotor, and then these beads basically get thrown around that milling chamber at very high speeds and a lot of force. So what happens there is actually that the particles that you can see, these pigment particles, actually getting pushed away as these beads collide at these high speeds. And that pushing effect, it's almost like when you're in a bathtub and you play with a rubber duck, and you try to squeeze or catch the rubber duck by squeezing your hands together. The rubber duck always tries to escape. And that's kind of what happens in a bead mill. And that action actually is what's causing those binding forces to break up and basically reduce those larger agglomerates down to smaller particles. That's how you have to envision what is actually happening in a bead mill. It's not that the beads are colliding together, crushing those larger particles, and that's what's causing the breakup. That's not really what's taking place. It's strictly the shear force of these beads colliding with high kinetic energy and really forcing the larger particle away, breaking it up as a result, and then turning those larger particles into these smaller particles. So that's what's really happening inside of a bead mill. So it's important to always remember that kinetic energy is really what's making what's important, or one of the most important factors in the milling process. And here's just a calculation of how you figure out the kinetic energy. If you want to write it down, or we can share the slides later on for you to download. So the bead weight is very important. Obviously, the higher the bead weight will influence our kinetic energy. And so here's an example. If you have, it's like small beads, it's a small hammer, And if you try to nail that, draw the nail or drive the nail into the board, and you have only a small hammer, it will take a long time to really put the nail into the board. And depending on the size of the hammer, the size of the nail, it may not even be enough to really get the nail driven into the board. So the larger the hammer, the easier it will be to drive the nail into the board. So that's kind of the same philosophy when we're talking about milling. So if we have heavier beads, we are more successful in breaking up the binding forces because we have more kinetic energy. If we optimize the speed of our rotor, then we would use beads with less weight or smaller beads. So that's something that you always have to keep in mind. We have customers that are talking about, we want to get inexpensive beads. We like to buy glass. Yep, that's great. Glass beads are really easy to get. They're cheap. But the problem is when you look here at this chart, the glass beads have specific weight of only 2.5, whereas the zirconium oxide serum stabilized are almost 3 times as heavy. So there's a lot more force that can be applied by using just a ceramic bead. Obviously, the hardness also plays a really important part. The glass beads have only a 400 Wickers, and the zirconium oxide bead almost 1200. So they're almost 3 times harder than glass. So what that means also is when you're running glass beads over time, the glass will wear much faster, and you also will end up with shards that tend to break up easier. And then you have glass shards in your slurry that you have to filter out and basically replace them, and they also wear very unevenly. So it's a much better solution to really use better quality beads. In the long run, you will spend a little bit more money up front, but you will use a lot less, and your process will be a lot better and more stable than using the inexpensive glass beads or some other options that are on the market. And keep in mind, there is also a lot of different bead suppliers. We offer beads. We have really good high-end ceramic beads in our portfolio, but certainly you can find some lower cost options. But when you buy these beads, always ask for maybe from a supplier that you're not familiar with for a sample, and then look at them under the microscope, because a lot of times what we have found is that some of these beads are inexpensive or relatively inexpensive, but when you look at them under the microscope, they're not perfectly round. And that's also a problem. The beads should really be spherical and almost perfect. When you get your hands on really inexpensive ceramic beads, sometimes they're not always perfectly shaped. Some of them are oval. We have seen some of them that actually have edges and cuts in them. You can throw those away because they will also cause uneven bead wear, and you will end up with a mixture of different size beads. Therefore, you're not really able to always replicate your process ideally. So you always want to get high quality beads and pay a little bit more money for them. So here's a great slide here. We can actually see in these corners right there, that's where we're actually breaking up these binding forces, and these larger particles really get reduced to the smaller particles, ideally primary particles. So these are some of the critical parameters that we have to watch out for. Very important. Before we are milling, we should do a grind check to make sure we are in the 10 to 20 micron range. Otherwise, we still need to continue to pre-disperse before we start to mill. What happens if you're putting, let's say, poorly pre-dispersed material into your milling chamber? You have a screen in the aerodynamic gap. If the particles are too large, you will have a clogged screen very quickly. Then you won't have flow through the mill, and that's also causing issues. You're not going to be successful milling your material. So you should always make sure that you measure your particle size before you start milling to know, number one, what screen to choose, and also what type of media you should pick, the size of the beads, to have the correct setup. Otherwise, you end up with a clogged screen, or your milling process is hindered by the size of your beads, not enough kinetic energy. Because if you take a standard bead is 1 to 1.2 millimeters with the 0.5 screen. That's where we usually start out with if our particle size is between 10 to 20 microns. But some people want to go down to nano, and then they throw in 0.2 millimeter beads. Obviously, there is nothing going to happen because the 0.2 millimeter beads are not heavy enough and big enough to really break up these large particles, 10 to 20 microns. So you really need to work your way down before you can use those smaller beads. So it's really important to always watch that. The amount of beads, so each of the different milling technologies has different fill rates. The shape of the beads we already covered. Tip speed, again, very important, 10 to 16 meters per second when you're milling. Product temperature, extremely critical when you're milling. There is a lot of energy that gets built up in the milling chamber or in your supply vessel if you have circulation, and that also needs to be cooled. So that's really important. Energy input, how much energy I'm putting into my mill base when I'm milling. So some of our medium mills allow you to not only run with a certain speed, but also allow you to run with a certain amount of energy. So then the speed would adjust depending on the viscosity of your mill base to always maintain the energy that you are trying to put into the slurry. The number of passes is important. How often does my mill base circulate through my milling chamber or basket mill? Milling time. Usually the longer I mill, the finer my material. The viscosity of the mill base, again, really important. Sweet spot 1,000 to 5,000 centipoise. We can obviously mill with high viscosities, no problem, but we may have to watch out how we get the mill base into our or through the milling chamber. So there are different technologies that can help us. Milling tool diameter, how big is my rotor? What type of material am I going to use? Standard is stainless steel. The problem, though, with stainless steel, while it's relatively inexpensive, it will wear quickly over time, and you will end up with a sometimes, or most likely, if you're running white product, with tiny particles that are basically worn off, metal particles that are worn off from the rotor and the milling chamber. And these tiny metal particles would end up in your slurry. So if you're making a TiO2 slurry or white with some TiO2, that tends to turn gray. So you should always look at ceramic as an option to avoid that problem, especially for light colors. There is also the option of hard steel, which would still give some sort of a discoloration for lighter products, but it won't wear as much as a stainless steel. There is different ceramic option, obviously the white ceramic, zirconium oxide, or silicon carbide, which is a black ceramic. It's a little bit harder and also doesn't wear as fast. But these are some of the different options you should review before making a purchase, what would be best for your material. Also, compatibility is important. For battery technologies, obviously you don't want any metal whatsoever in your slurry. So therefore, it's imperative to use ceramic. Otherwise, your product will not perform the way it's intended to. And then obviously the type of milling design. So we have the vertical bead mills and the horizontal bead mills. So we'll go through that shortly. So just quickly, the great thing about a Dispromat is that it allows you to be fully flexible by adding different attachments. So in this case, the Dispromat functions as a disperser. But here on the bottom right, you can see the TML. That's just an attachment that would go right on it with the quick change system. So I can turn the Dispromat dissolver into a basket mill within less than 1 minute. So that's awesome. I can also attach an APS system, which is a vertical bead mill, which is a wonderful milling system, allowing you to quickly mill small samples, and it's very easy to clean. So this is a perfect solution for the lab. We'll talk a little bit about that as well. You have the ability to add a rotor stator. Some people like to use a rotor stator to break up agglomerates, and successful with it. There is a wall scraping system available for really viscous materials, and some people like to disperse on the vacuum. So we also have a CDS system available that allows you to do the process on the vacuum, pre-dispersing, but also milling. So here's just an example of a Dispromat. This is actually our flagship model right here. Can go up to 20,000 RPM for the small benchtop units. And that's here is outfitted with the cowls blade. And on top right here is the quick change system that called the DL shaft. You open the clamping ring, turn it assembly 180 degrees, pull it out, and just replace it with the basket mill or attach a vertical bead mill. So it's really simple and easy to move from one system to over to another. We also offer explosion-proof versions, depending on what type of material you're running. Solvent-based. We in our lab don't have any X units. We have them inside of a hood that basically draws away all the vapors. And so therefore we can't really have an explosion. And it's also a little bit more cost effective than installing an explosion proof unit. We have some customers that call in, they need explosion proof. That's great, but when we actually look at where the unit's getting installed, we find out that it's not even ideal because the light switches are not explosion proof. The viscometer next to the Dispermat or the milling system is not explosion proof. So the question comes up, why you're putting a milling system with a Dispermat into a laboratory, an explosion proof system into laboratory that is not explosion proof. So always make sure you answer all these questions beforehand before you make the investment into buying an explosion-proof Dispermat. Because they're quite a bit more money, about 30% more in cost, and you may not need it if you install it inside of a hood. So again, the Dispermat can be used as an homogenizer, emulsifier with that rotor stator, or as a disperser with these different attachments, these basket mill attachments or vertical APS system, as well as just the standard dissolver disc. So here is the TML, which is our basket mill. Fantastic milling system. Our units are double walled, which is really important because this is the milling chamber right here. That's where we put our beads. You can see the yellow part here is our milling disc. Right above is the pumping wheel that actually draws the mill base into the milling basket. And then right below the milling disc, we have a screen to let the material flow back out into the container. And that cowls blade that sits on the bottom of the screen actually supports that by actually drawing the mill base out of the milling basket through the screen and back up to the top, where then it gets sucked back into the basket mill. So you have a really nice flow and circulation of your slurry in and out of the basket. Very easy to clean. That's a big bonus because when I'm done with my milling process, all I will do is I remove the container, put another container there, fill it up with cleaning solution with the right solvent, and then just immerse my basket again and run it for 5 minutes. And that does a pretty good job of making sure that my mill is properly cleaned. Sometimes it takes 2 or 3 cycles with just refreshing the solvent or cleaning agent to really give it a good wash. And that usually does a good job. If you want to then do a better cleanup, then you just open up that screen on the bottom. You would remove, obviously, that cowls blade, and then the beads would fall out. Put a little catch pan right below where the beads can drop in, and then you would put those into a bath, like an ultrasonic bath we have in our lab that does a great job really cleaning those beads really well for your next trial. And then again, the double-walled basket is really critical and important. I can't stress enough how important it is to cool this milling chamber properly, or you're going to get issues with deformed milling discs, melted milling discs. We've seen a lot of issues if that's not properly cooled. And again, with the basket mill, what's great is we can also mill down to the nano range by attaching a nano kit, which allows us then to put a small screen right there, 0.2 millimeters, 0.1 millimeter screen, and then we can actually go down to 0.2 millimeter beads. We have made custom screens even smaller, but that really depends on how small you want to go. These options exist. Here is a great slide showing you kind of the flow of the mill base, slurry in and out of the basket mill. So here you can see it's filled with the beads. The slurry gets drawn into the basket through that pumping wheel. The milling disc takes over the action of milling with the beads. And then that cowl blade on the bottom actually draws the mill base back out and pushes it back to the top. Well, then it gets sucked back in. So you have a very nice circulation of your slurry in and out of the basket. That's really important. You want to have as many cycles as possible, and that will give you a smaller particle and a more uniform and narrow particle size distribution. And then here you can see when I'm pulling up my TML, I would, on top of the container, because we recommend the 50% fill rate, I would then run it up here for like a minute or so, just to get rid of the excess material, get it out of the milling chamber, and then replace that container with the mill product with the new one with the solvent or cleaning agent. And then re-emerge that mill down into the pot with the cleaning agent to clean. Great design. Here is a large one for production scale. Again, double walled. Here, the way we cool the basket is with these bars right here. So we have water in, or glycol in, or whatever cooling agent you want to use, and glycol cooling out. On the back right here, there's a third bar rod that actually is used to measure the temperature. On our production machines, we're actually measuring the temperature inside of our basket mill, which is really good because that's where most of your energy is created and built up. Your temperature rises tremendously right in here. And so we want to measure it right there because we don't want to damage the product. And that's how we will also want to decide or use that information to set up the parameters on our chiller that we need to use to really make sure that everything is properly cooled. On the production scale, we have a port right here with a screw for our bead loading. That's where you would put a funnel, and then you put the beads through the funnel into the milling chamber. A very easy way of doing it. Okay, so again, some of the core key features of a TML is that it's a batch system. So you're going to be stuck with whatever you have in your container. So that's one of the drawbacks. So there is no like a pass-through system like on a horizontal mill. But the advantage is it's very simple design. You don't have any bearings. You don't have any seals. There is no really wear parts except your milling disc and your pumping wheel and your screen. So these are really the only parts you need to replace periodically. But on a horizontal mill, you obviously have a lot more wear and parts that you need to replace periodically. And also cleaning is a lot easier on a TML than on a horizontal mill. So we have actually a lot of customers moving away from the horizontal mill design because they really like the simplicity and ease of use of a basket mill. But you have to remember that if you have really high viscosity and the material doesn't flow properly, then this is not a good solution because the material will not go inside of the basket. So it really is important to ensure that you have good flowable material. We have customers in excess of 1,000 centipoise that are still able to use a basket mill as long as the material is flowing. Again, very easy to handle. The double wall is really important. And then I already talked about the ability to add a nano cape. Here is a larger one for production that you can see on the right. Great system. We also offer it with vacuum. Some people like to use a vacuum, especially in production, because it allows them to remove the air and then have less foaming, and that allows them to quicker transfer material from one container to another container, like a holding tank. So that's a key feature, is that vacuum. Obviously, it comes at a price, but in some situations, customers really need it and want it. Here is a great system. This is called the Dispromat TM for production. This is a combination system. So you have actually a system that has milling capability and dispersing capability all in one. So you don't have to make any changes. So the blade is actually right back here. They have not been installed yet. So they will go right on the bottom here. So what customer does is he pushes the container with the mill base to the machine, lowers the shaft with the blade, and then it does its pre-dispersing. When he reaches the right particle size, like 10 microns, where he would then normally move the container over to a different mill, he leaves the container there. Instead, he pushes a button on the control panel, and that basket up here gets lowered, and now this whole thing becomes a milling system. So it's incredibly efficient, very easy to use, and it's a dream for every operator because they don't have to move containers around. We have the Dispromat SC as an option that basically allows you to move the baskets as you need them and have basically a quick color change. So this system here is not ideal if you have to change color 5 times a day because it's harder to remove the basket. On an SC with the TML, it's very easy to remove baskets and replace them. And that might be better if you have a lot of different colors you want to run. So this customer here has 2 TMs. They run them 24/7, and they love them because they don't need any more media mills, so everything is done on one machine. Huge cost savings, maintenance savings, and obviously space savings because everything can be done on one machine. Then we have obviously the vertical bead mill called the APS, which is a great system for the lab space. It's easy to use. So you have basically 2 containers. So you have your top container with your mill base or your slurry. You would pre-disperse in the same container. When you're ready to do milling, all you would do is you remove the cowl's blade and replace it with that milling disc. And then you would add your beads to the container, to the slurry. Push down the cover, and then start your milling process. When you're completed with the milling cycle, you would hook up the air hose to the socket right here, and then purge out your mill base through the container into the container below. There's a drain plug right down here that can be removed very quickly and easily. And then the screen that's on the bottom here would hold the beads in place inside of that container, and only your material will get purged and put into the container below. So it's like a filter system, and also a very quick way of getting the product drained out through that air pressure. And then when I'm cleaning, all I would do is remove that container on the bottom with my milled material, put the drain plug back in place, and now pour in some solvent or cleaning agent into my container on the top, put another cup down below where you want to drain the cleaning fluid, and then run the setup for a few minutes, and then basically drain it out, and then repeat, rinse and repeat, rinse and repeat. Eventually, it's going to be clear when it comes out, and your milling system will be perfectly cleaned. That's a very, very easy way to mill. The big advantage is obviously cleaning. Also, you're not limited to viscosity so much. You can go down really low in viscosities, almost like water, because you can add 100% beads. So if I have 100 milliliter of my slurry, I can add 100 milliliter beads. which this APS system allows me to have the highest bead loading of any comparable or any milling system out there on the market, which is great. So I can improve my milling efficiency, my milling time goes way down, and I'm also able to mill many different types of products very efficiently and effectively. So now, the drawback to this particular system, with all its beauties and advantages, is that it's really not scalable to manufacturing. There is unfortunately no large scale, really big, I'm talking 100 gallons, 50 gallons and up, 1,000 gallons, APS system that is available because of the design, and it would be very difficult to handle. Therefore, this is really an optimum solution for your lab space. We have, for one customer, built custom APS systems that basically go up to 5 gallons or 10 gallons of material. But these are specific circumstances. That particular customer makes a very expensive platinum paste. They have, in this case, a very high viscosity. They don't want to lose any paste, so here they know everything in the container stays there, and they can recover it easier. So they were willing to get a custom APS for the 10 gallons. But anything bigger than that is not feasible and not available. So, but it's a really great milling system, relatively inexpensive. Actually, if you were to look at a particle size distribution and particle size, this is very, very similar to a horizontal mill. And actually, the particle size distributions, you can get narrower than with the horizontal mill on an APS, what I've seen. So it's a wonderful milling system. Here's the slide showing you kind of how that, the graph, what that looks like, the slurry with the beads. You're milling this, and then when we're done milling, we just remove that drain plug on the bottom and purge it out. So it's a wonderful milling system. Another slide. Different types of milling discs available. So different types different materials. Steel, we have polyamide, we have Teflon, ceramic, so many, many different options. So great advantages there. Again, it's a modular attachment to our Dispermats. You can go down to really small volumes, down to 12 milliliters. Extremely fast, very easy to clean, really wide viscosity range. Obviously, we talked about that upscale limitation due to the lower volume. We can add a nano screen. Actually, there is now screens that are even smaller than what you see here. We have ceramic lined milling chambers, chambers in the pot, as well as tool, and again, easy to handle, very quick to clean. And then we have finally the horizontal bead mills, which are very popular, but again, needed in some applications. Some customers want to have just pass through, so you put your product in, go through the milling chamber, come out and collect the product, or you recycle, or you go from one horizontal mill to another horizontal mill to another horizontal mill, set up with different bead sizes. So we have customers that have 3 of these mills set up in succession, and it goes from one over to the next until the material reaches the desired particle size. So there's many different ways on how you can incorporate a system like this in your process, either in a lab space or obviously manufacturing. Again, great cooling capability with our SL. We have here the cooling on the milling chamber as well as on the supply vessel as well, because when the material comes out and goes back into the supply vessel, temperatures will be very high. So here we want to cool it down again. So that's why that supply vessel can also be ordered with a double-walled chamber. Right on top here, we have our agitator. It's a pumping and steering system that will force our slurry down into the milling chamber. So it's a really neat setup. That's actually the latest SL came out last year with that new C technology display. Really pretty machine, very effective. Again, the drawback is lots of cleaning time is needed. If you take it apart to clean this, about 45 minutes. To do a great clean, about an hour to an hour and a half. And again, there is a lot more wear on a machine like this and parts that you need to replace than on an APS or a basket molded TML, what we talked about earlier. So you can have the advantage there, obviously, pass recirculation method. It has an integrated pumping steering system, goes up to 6,000 RPM of rotor speed. Again, you can buy different linings or rotors are made of different materials. You have a nano kit available for very, very small particles. Just a couple different options you have in terms of control capability. This is true for all of our Dispermats or mills. So this is the new C technology package. That's great because it allows you to port data to a computer. You can see your RPMs on top. It'll show you right below the watts. That's the amount of energy you're putting in. It shows you your torque value, which is an indirect measurement of viscosity, your tape speed, your temperature, and your timer function. Now with the C technology, you can program it so that you can set up a recipe. You can give products a name or store it by batch number. And then basically you can replicate the process very easily every time when you recall the product. It'll use the same parameters to ensure that there is good reproducibility and obviously repeatability of the machine. And then we have the simpler version here, which is just the standard controller called the M version, RPM, amperage, temperature. That's actually for a production scale right here. Advantage is that it doesn't matter if it gets dirty, it's all sealed and more sturdy for your production environment. And here we have the PLC control. It's a special, some customers want to have their own control capability, allowing them to basically add a scale or other options and then have everything programmed, and they can customize the entire dispersion process. The downside is right now, I found out a couple weeks ago, the lead time on this PLC controller right now, I think is 1 year because they can't get the components. It's just really unbelievable right now how difficult it is to get these parts. Just a quick slide showing you how on the C technology you can control it, what it shows you. Again, everything can what I described in the display, but you can also program these cutoff values, meaning if the temperature goes to a certain point, or if you if you run with constant power and then the speed will go out of a certain range, you can program these cutoff values, and then the machine will actually run either at a different speed or shut down altogether. As you can see on the top right, this is just an example. And then you can actually visually see the dispersion process in a graphical interface that is displayed also to give you a trend line for each of these important values. So you can see right away if there is an issue during the process or something goes out of range. That all that data could also be ported to a computer, and you can monitor the entire dispersion process there in real time and store it. We can also do what's called a net power calibration with the C technology, allowing you to basically to set everything to a zero value. So imagine when a mill runs on its own without product, it already uses a load and basically torque values, just from moving the rotor, from running the energy that's being put in. So all that will be set to a zero value. So when you run your product and you look at the torque value or the energy input, is strictly then related to dispersing your material and not including the energy input of the machine. That can be very helpful, especially when you want to go upscale. That's what the old WinDiff software would look like. We're actually right now working on replacing it there'll be a new WinDisp. So that was the software that allowed you to monitor and actually somewhat control the dispersion process remotely from your computer. And then we have obviously laboratory capabilities in Germany. It's a great lab. We have a vacuum system with any Dispromat you can imagine is in that laboratory, even for manufacturing upscale. And we have a smaller lab space in Wallingford, but we also have another lab that we're opening in Columbia, Maryland, that allows us to do trials. And we added some new capabilities right there. So that's the new AE6 flagship disperser we have in Wallingford, and we also have an SL12 that you see right here. So both machines are in Wallingford, and with all these different attachments. So we have them up here, different milling system, rotor stator, vacuum system, APS. So if you want to come up to the lab and look at the equipment and do a trial for your material or with your material, be our guest. We'd love to have you. The advantage again is we'll invite our chemists from the additive team into the meeting. They're going to be present during the trial, and they can give you formulation recommendations or advice on how to optimize a formula or improve certain characteristics of your material, whether it's coatings, paints, battery, slurries, any type of technology or end use market that you're working in. We can help you. We have a lot of different scientists that are familiar with these type of materials. So it's a Class A facility used to really show you all these capabilities. Great for upscaling experimentation, and it can come in just to look at the equipment. We don't have to run your material, and we can use it also as a seminar location if you want to bring in a group of your scientists, or you have new people working in the lab and you want to give them, a course on milling and dispersing. We can set that up as well. So we have all these capabilities. I want to thank you guys today. Appreciate everybody's attendance, and hopefully this was valuable.
Yeah, thank you, Andy. Very good, always informative. We have a couple questions here. I know we're running short on time, but let's see if we can get through them. First one, can milling fracture or break agglomerates by collision, or does it only deglomerate due to shear field near a moving bead?
Yes, that's correct. So we did this, we looked into this. It actually is interesting. There's the probability of actually destroying a pigment particle or an aggregate is very small. Again, I get back to that rubber duck syndrome. It's hard to get that rubber duck caught right in the middle when you're pushing your hands to get in the bathtub. So that kind of what happens in the mill. Of course, there's going to be, just so it happens, that a pigment is going to float by, and exactly at that point, it's going to get crushed by two colliding beads. But that is not what usually happens inside of a bead mill. The probability is very small.
Okay, thank you. Next one. How does bead mills compare with rotor stator concentric tooth shear disperser?
So they are available. There's, I think, a French company that makes them. We have not for production. They're used. They're easy to use, but there's also limitations in terms of particle size. The viscosity has to be really specific. They usually very low viscosities to optimize the rotor stator. And we have customers that are going away from the rotor stator back to the milling system because they think that they have a more narrow particle size distribution. I think there's a company called Instral that makes them. But again, everybody has a different application, but most customers would stick with traditional bead mills.
Okay, another one here. Smaller beads mean more shear events. Is that a correct statement?
Smaller beads means more shear events. Actually, that would be a correct statement, because if I have smaller beads,
yeah,
I fill my milling chamber based on volume. And when I have, larger beads, and based on volume, I'm gonna have less beads in my milling chamber. And when I fill smaller beads, I'm gonna have more beads. Therefore, I should have more more shear action based because I have smaller beads. Now, but be careful, the kinetic energy is far less on smaller beads. So if your particle size is too big and you put in small beads, you're not going to be effective in milling, even though you have more shear action or more shear events, if you call them, because they're not going to still have enough force to break up these binding, these van der Waals forces, to turn these larger aggregates down to the primary particle size. So smaller is not always better just because you have more events.
Gotcha. And the last question here in the home stretch from Andrew. Do you have to optimize milling conditions for each pigment, or will one set of conditions fit a range of pigments?
Yeah, usually it's not. The pigment is the issue. It's more like the formulation of your dispersion, right? So pigment dispersions can really vary depending whether they're for coatings, inks, plastic concentrates. So there's a wide range of different formulas. So you really optimize not just for the pigment. Sure, certain pigment classes, right? For example, carbon blacks. They you really have to mill them down very, very fine to get the most yield or be most efficiency out of them, right? So carbon blacks, obviously you want to optimize that by using a nano kit preferably, and then milling down as small as possible. So that means different size beads, and maybe also different milling trim. You don't need maybe necessarily. Well, you will need ceramic because you're nano milling, so that's not an option. But if for standard pigmentations, not really an issue. It's more a question of the type of formula that you have.
Great. Thank you very much. And thank you, everyone. In the chat, I did put Andy's email address. Feel free to copy that down. If you think of anything after the fact, feel free to email him. You'll also receive an automated email from marketing with the link to the recording. If you have questions, you can always hit reply to that. That'll come to one of my colleagues, and we'll route it to Andy or one of the experts in your region. So with that, thank you, Andy. Very informative, lots of great information to round out our dispersion and milling series, I guess. Thank you to everyone attending, and hope you learned something, and stay tuned for future Bic Gardner web seminars. Thanks, and have a great rest of your day.
Thank you very much, everybody. Have a good day.